So, in the last class when we are talking about the two dimensional maps, we had seen that the essential idea is that we are placing a Poincare section, and if the original system is 3 dimensional, the Poincare plane is 2 dimensional. So, we will see things on the Poincare plane, that means we will obtain 2 dimensional maps in this form x n plus 1 y n plus 1. This is some function of x n y n, and this is some other function of, and then we said that having obtained this, the next step would be to obtain the fixed point by substituting x n in the left hand side. That means, the fixed point is the one where the x n plus 1 is equal to x n, y n plus is equal to y n. So, if we substitute, we get a pair of equations, 2 equations, 2 unknowns. So, we can obtain that. So, we can obtain the fixed points, and the next step was to obtain the local linearization in the form of the Jacobian matrix that we have done. Having done that, what we obtain is a linear equation x n plus 1 y n plus 1 is a matrix times x n y n. This matrix is the Jacobian matrix. Then we said that the next step is to obtain the eigenvalues of this matrix and eigenvectors, and depending on that, if the eigenvalues are real, then the eigenvectors, else there is no point in obtaining the eigenvectors. So, when we do that, in the next stage we say that it is now possible to understand the dynamics in terms of the eigenvalues and the eigenvectors. Like we managed to give some names. We had said that supposing here is a fixed point and here are 2 eigenvectors, if both the eigenvalues are positive and real and between 0 and 1. So, 0 less than lambda 1 comma 2, then their behavior would be like this. From here also it would be approaching. So, this would be called, what was the name given? Regular attractor. What would be the behavior if you start from somewhere else? How will it proceed? Obviously, this will approach the fixed point, but how? Again, try to remember recall the logic that we had given earlier. This has to be broken up into 2 components along the 2 eigen directions, and then this distance will progressively reduce as multiplied by the eigenvalue along this direction, and this one will reduce as multiplied by the eigenvalue in that direction. So, if say here the eigenvalue is 0.1 and here the it is 0.8, how do you think it will proceed? This one will be multiplied by 0.1, therefore, it will shrink fast, while this one will be multiplied by 0.8, it will shrink slow, as a result of which it will go like this. Okay. So, this is the regular attractor, and if we have the eigenvalues, say what is it called? The one eigenvalue is between 0 and 1, the other eigenvalue is greater than 1, it is a saddle, it is a regular saddle. So, the behavior would be, if this is the lambda 1 direction, it is contractive, while if this is the lambda 2 direction, it will be all the time. Try to figure out how the behavior will be if the initial condition is placed elsewhere, not on the eigenvector. You should be able to visualize that. Next, what if you have then flip saddle, because this is less than -1, it is outside, its magnitude is greater than unity. So, this is saddle and this is negative, therefore, flip. So, how will the behavior be? If this is the regular direction and if this is the flip direction, the behavior would be like this. Okay. It will actually go from one side to the other and therefore, it will be flipping. This is a flip saddle. This is what we have done. Now, apart from that, can you figure out what other possibilities are there? There can be flip attractor, of course. Flip attractor would be where the eigen directions are 0 less than So, how will the behavior be? In one direction it would be like this, in other direction it would be, but nevertheless coming closer. Okay. So, these are the possibilities when the eigenvalues are real. This is flip attractor. What happens in these cases? You normally say that it goes out to infinity, right? But remember that actually does not happen. Why? Because this is only the local linearization, this is only the local behavior. So, you might say, you might at most scientifically say that this particular set of iterates go out, go away from this particular fixed point, but you cannot really say that it goes to infinity. We will come to that later, what can happen to such systems. But let us now tackle the case of complex eigenvalues. So, complex. So, lambda is equal to a, what will the behavior be? Say this is our axis and say this is our initial vector x. Obviously, as a result of the multiplication with that matrix, this vector will be operated on by a complex number, and that complex number can be also written as, say, lambda real or magnitude angle some theta. So, the moment you write it like this, you recall your ideas you learnt in the first year electrical circuits course. You remember, you understand that as a result of the multiplication with this, what will happen? This vector will be multiplied by the magnitude and it will turn, it will rotate counterclockwise by the angle theta. Okay. So, what is this lambda? Lambda is and the angle is okay. So, as a result of this, what will happen? If this root over a square plus b square or the magnitude of lambda is less than 1, then it will become a smaller vector and it will turn by an angle. Okay. What will be the result of repeated application of this? That means, if you are keeping on iterating this, what will happen? In every iterate, it will rotate by theta and it will shrink, and as a result of which you will get a spiral, incoming spiral. But remember, it is not a continuous motion as you had encountered while dealing with the continuous time systems, differential equations. This will be like a set of points that go jumping like this, but ultimately converge. Are this point visible on the screen? Okay. So, this would be a incoming spiral behavior. Likewise, if you have the root over a square plus b square term, the magnitude of the eigenvalue greater than unity, then it will be outgoing spiral, obvious. So, there are two possibilities for this would be incoming spiral for lambda less than 1, and if it is lambda magnitude greater than 1, then it would be so on and so forth. Okay. So, these are the two additional behaviors. This is the incoming spiral, and this is the outgoing spiral. Now, notice that these nomenclatures pertain to these points, right? The fixed point has the nomenclature. In these cases, the fixed point, the one that is around which you have this either incoming spiral or outgoing spiral behavior, these are called foci. That means each one is a focus. So, this focus, this specific term is used where the eigenvalues are complex conjugate. It could either be a stable focus or an unstable focus. If one says it is a stable focus, you know that the behavior around is the incoming spiral, and if one says that we have a unstable focus, you would understand immediately that one is talking about the behavior that is a outgoing spiral. Okay. So, we have now understood the types of fixed point that can be there. Now, we had said that we are ultimately trying to understand the stability of periodic orbits by placing the point cross-section and looking at this. And stability obviously now can be understood in concrete terms. What is the concept of stability then? In these cases, when under what condition was the fixed point stable? In these cases, see, yes, the magnitude would be between 0 and 1 is a you are talking in terms of real, right. If it is complex conjugate, then the magnitude has to be 1. So, actually it will boil down to whether or not the vector itself, that means the complex number itself, is inside or outside the unit circle. Okay. If it is outside the unit circle, it will be unstable, but you can now relate the positions of the eigenvalue on the unit circle or in the Eigenvalues as written. Because whatever the behavior is, two of them are here and here. Quick, flip attractor. Yes. What will be the behavior if they are here? Focus. It is a stable focus, incoming spiral behavior. What will it be if this and this? Saddle. Okay. So, the stability condition, now you have to remember that the stability condition is different from what you had in case of continuous time dynamical system. In the earlier case, you had the eigenvalues, the real part would have to be negative, but here in this case the eigenvalue itself has to be inside the unit circle. Now, if I ask you, in how many possible ways can such a system lose stability? In how many possible ways? Means essentially that will boil down to in how many possible ways can an eigenvalue exit the unit circle? It is not difficult to see. There are exactly 3 possible ways. One, say the unit circle is like this, and it goes like this. It is possible. Another possibility is where you have the unit circle like this, and one eigenvalue goes like this, and the third possibility is a pair of eigenvalues leave the unit circle like this. These are the three possibilities. Okay, fundamentally different possibilities. Obviously, it could go this way and could go this way also. There is no fundamental difference between them. That is why these are the fundamentally different ways in which a fixed point can lose stability. So, let us try to understand each of them, what happens. But from our earlier concept of one dimensional maps, can we relate what is happening here? An eigenvalue is becoming -1. What is our anticipation? In case of the one dimensional maps, what happens when the slope becomes -1? Period doubling bifurcation, right? All these are bifurcations, because in all these cases the fixed point is losing stability, something else is gaining stability, and so you have bifurcation. But in this case you anticipate a period doubling. Why? Because of the similarity of the situation with the one dimensional map. But whether or not that happens, we need to check. In this case, eigenvalue becoming +1. What happened then? Tangent bifurcation, or we called saddle node bifurcation. Yes. And the third we did not come across, because in one dimension system you cannot have a complex conjugate pair of eigenvalues. So, these two we recall what we learnt in 1D and try to extrapolate it in 2D and try to understand what is happening. Now, let us try to understand each of these in terms of, okay, let me write down the name, because here we understood that this should be the period doubling. We will prove, but yes, it is actually period doubling. This is saddle node, and this is a special situation which is similar to, okay, I will treat this a little later. It is called a Nymark-Sacker bifurcation. First, let us handle these two, and then we will come to this one.
So, why is the saddle node, which is referred to as saddle node, also assumed to be Pitchfork, because Pitchfork bifurcation also occurs when the eigenvalue is plus?
Yes. His question is, we had seen that the Pitchfork bifurcation also occurs when the eigenvalue becomes +1. Pitchfork is what? Do you recall? Where the bifurcation diagram would look much the same like the period doubling bifurcation. Only thing is that in period doubling, what is created a period 2 orbit, while in this case what would be created is are 2 period 1 orbits, both stable. Okay. I also said that they are somewhat rare situations, so this similarity and other things, as I told you, that it comes sort of intuitive prediction. It might not be true. You might argue that no, it should be similar to the Pitchfork bifurcation. Yes, true. That is why we need to examine each case separately, and after having examined, if we find that it is similar to the tangent bifurcation case, yes, then we will be convinced. Before that, do not be convinced. Okay. Okay. In order to explore, let us explore by means of a specific map called the Henon map. This map is x n plus 1 is equal to a minus x n square plus b, and y n plus 1 is equal to 2D system. So, when we proceed, what would be the first step? To locate the equilibrium points. Do this. Let this be an exercise that we do today, so that we will trace all the steps that we need to do in order to understand the behavior of a system, and the first step is to locate the equilibrium points. and in order to locate the equilibrium points, we will have to set fixed point. Let the fixed point be x n x star. So, we would write x star is equal to a minus x star square plus b y star. X star y star is the fixed point, and y star is equal to, substitute it here, you get a quadratic. Fine. Let us proceed by choosing one of these parameters. There are two parameters a and b. Let us choose one of these parameters. Say, let us set b is equal to 0.4 and a variable, and we will be trying to understand what happens as a varies. Okay. So, that this fellow is now 0.4. So, you have the, if you substitute, what is the equation you get? Let this go to the left hand side, x star square, these two gets subtracted. So, you have plus 0.6 x star minus a is equal to 0. So, the x star is half minus 0.6 plus minus root over b square 0.36 plus 4a, right. For the sake of simplicity, let us take 4 out and cancel this. So, this is equal to minus 0.3 plus minus root over 0, this will be 0.9. Fine. Now, this immediately tells you that so long as a is less than 0.09, the position of the fixed point is you get complex number. Position of a fixed point cannot be a complex number, and therefore, it does not exist. So, the fixed point does not exist for right. Now, suppose we are varying the parameter and say we are varying the parameter a and we are varying this way, and here is 0.09 minus 0.09. Before that there was no fixed point. Beyond that, what will happen? There will be two fixed points and their locations are given by x star 1 and x star 2, because by virtue of this you would say this is also y 1 star is equal to minus 0.3 plus minus root over 0.09, not plus, this only the plus a, and y 2 star is equal to minus 0.3 minus, fine. So, these are the two fixed points, which means that beyond that two separate fixed points are born. Is the point clear? It is not that one is born, two are born, fine. So, these two are born. Now, we need to find out what they are, what kind of behavior do they have. How will you do that? We have to take the Jacobian and we have to study each one individually. So, this equation you take the Jacobian, this is your f1 x y and this is your F2. So, what will be the first term? First term would be minus twice xn. So, the Jacobian is minus twice x star. Second one is F1 with respect to y, which is b. We have taken it as 0.4. The third one is F2, this with respect to x. So, 1, and this value is 0. In the next step, we will try to investigate this and that separately. So, first substitute this here, right. So, what do you have? Its characteristic equation would be, let's first determine it in terms of this. So, it would be minus twice x star minus lambda, here this minus lambda. So, minus lambda minus twice x star minus lambda minus 0.4 equal to 0. Okay. So, you have lambda square plus twice x star lambda minus 0.4 equal to 0. So, you have lambda is equal to minus x star plus minus root over x star square plus 0.4. Okay. Fortunately, here we have a square term. So, we can substitute here and make it simpler. So, just substitute this one here and see what is the result. What are the eigenvalues in these two cases? Well, wait a minute. First, let us assume A is equal to 0.09. Okay. If A is equal to 0.09, then this term vanishes. So, you have both one, have 0.3, put it here, and you have, just put it here and see. What is lambda? 9. Wait a minute, it was minus 0.3 here, you are substituting this. So, this fellow goes to 0, minus 0.3. If you put minus 0.3 in front, there is a minus, how can you get? Yes. So, you don't give me the wrong feedbacks, it cannot be negative. So, if you substitute this at A is equal to minus 0.09, this is at A is equal to lambda is equal to minus plus 0.3 plus minus so 1. Okay. So, this is the point that I was trying to drive at. You see, at that value, one of the eigenvalues is exactly 1. So, does that answer your question now, Manjul? Yes. So, here the eigenvalue was plus 1, but at the same time the phenomenon that we observed here was that at this parameter value 2 fixed points begin to exist, these 2 fixed points. Before that it was not, they were not there, after that they were there. Now, the next point is when they begin to exist, that means when they are existing, what are they? We have already categorize different types of fixed points, which category do they belong to. In order to find out, we have to choose a value of a slightly bigger than this, and a nice choice would be a is equal to 0, okay, slightly bigger than this. So, choose if you choose a is equal to 0, the advantage is that this is now you can take a square root, do it. It would be minus 0.3 plus 0.09 so 0. This is equal to y1 star. So, one fellow is situated at the origin, the other fellow is situated at is equal to. So, if you have this as the state space, one is here, another here, right. Fine. What are they? For that, you will need to substitute them here. So, when you substitute the position of the first point, which is x1 star is 0, if you substitute it here, you have for this one what? Plus minus? Is that right? Oh, root 0.4. Okay. .4. Okay, that's possible. And this fellow is if you put 0.6 here, it would be 0.36. So, 0.6 plus minus root 0.76, is it? Whatever it is. The point I am driving at is this fellow is surely both are within the unit circle, right, and this fellow is one is outside the unit circle, the other is inside the unit circle. So, this fellow is a attracting fixed point and this fellow is a saddle, attracting node, and this fellow is saddle. So, the two things that have been born are a saddle and a node. That is why it is called a saddle node bifurcation. Okay. So, the meaning of the term saddle node is clear only when you look at the two dimensional system, but the same phenomenon, since that also happens in case of the 1D system, it is also called a saddle node. But there is no really a good explanation of the term saddle when you talk about 1D. It is either stable or unstable. But in case of a 2D system, there are various types of unstable things. It could be a outgoing spiral, it could be a saddle. That is why when you talk about saddle, it becomes more clearer. Okay, so you have this fellow stable, this fellow is unstable. Which one is stable? This fellow is stable, and this fellow is unstable, right? And a flip saddle. It's a flip, right? It's a flip saddle. Good. Now, as you change the parameter further, what do you expect to happen? That there these two fellows will shift in position, because the positions are dependent on A. As you change the A, these fellows will shift in position, but since all the time x and y's are the same, therefore, all the time their position will be on the 45-degree line, but nevertheless their position will change and also will change their stability status, which means this. Now, can you find out, here is there was a fixed point which was stable. As you change the parameter, you do expect at some point of time they will it will lose stability. When will that lose stability? Can you find out? Rather simple really, because all you need to do, supposing you want to find out whether that fixed point undergoes a period doubling. Period doubling means -1. So, all you need to do is to put -1 here and find out when does that happen. Okay. Can you trace back and do that? The next question we are asking is, so if we conjecture that it loses stability by having one of the eigenvalues reaching -1, then all that we need to do is to find out under what condition, under what value of the parameter a would that happen. So, here you put -1, the negative thing will happen, and it is logical to say that in that case you will have to take the -1 here. There are two eigenvalues, plus and minus. The one with the plus will be more to the positive side than the one to the minus. Therefore, if one goes negative, then only this fellow can. So, you will have to substitute it like this: -1 is equal to minus x star minus root over x star square okay. So, what is the solution? Yeah, for first you need to find out x, and from there you need to find a. So, x is equal to x star is equal to 0.3, this tells you 0.3, and that tells you a is equal to, okay, referring back here. So, you know that as you change the parameter further at 0.2 at 0.27, the other phenomenon will happen where one eigenvalue reaches -1. Okay. What do you anticipate? Should be a period doubling, but in order to make sure, in order to convince yourself, what you need to do? You need to find out the second iterate of the map and find out its eigenvalues. Second iterate, finding the second iterate and finding the eigenvalues, by now you should be accustomed to, because it came in the mid sem. So, by now you should be accustomed to, because I found that some of you could not eliminate those known fixed points. That gave you some trouble, but should not give you trouble. So, all you need to do is to find out the second iterate of the map, which would be to be obtained this way: x n plus 2 is equal to a minus x n plus 1 whole square plus 0.4 y n plus 1, right. Then y n plus 2 is equal to x n plus 1. In the next step, substitute x n plus 1 y n plus 1 here. X n plus 2 is equal to a minus what square? This fellow square, a minus x n square plus 0.4 y n square plus 0.4 x n. Y n plus 1 is equal to 0.4 x n. Y n plus 1 is equal to x n, Now, y n plus 2 is equal to x n plus 1, which is a minus x n square plus 0.4. So, you have got the second iterator of the map. Do you? How to find out the fixed point of this? You would notice that it is getting a bit messy, because this will give rise to a fourth order term, but nevertheless, since you know that earlier two fixed points are still there, therefore, the same step, eliminate them, find out the fixed point, find out the Jacobian of this, and find out whether they do exist or not, and then if they do exist, whether they are stable or not. Okay. I have shown you how to do it, but do it and convince yourself. And let us not do it here, because though this is tractable, it will take somewhat longish time for me to do it. So, I leave you to do it. If it comes in the exams, you should be able to do it. That is the point. Okay, so we found a sequence of events that happens for this one, and in that process we understood two phenomena, that when the eigenvalue, one of the eigenvalues becomes exactly equal to 1, that is when a saddle node bifurcation takes place. A saddle node bifurcation means a saddle and a node are born. Now, suppose you are at a parameter value at which you have a saddle and a node both existing, and you change the parameter in the opposite direction. What do you observe? That they will come closer to each other. As they do, their eigenvalues, they also come close to each other, and finally at that particular bifurcation point of the parameter value, what will happen is that they will collide and disappear, and when they collide, both the eigenvalues will become +1. Okay. So, you do not really talk about the eigenvalue crossing +1. So, this representation is somewhat erroneous, it does not really cross, it does not really cross, it does not happen. What happens is that this is the unit circle, it goes, hits and disappears, all right, but it does cross through the negative, it does cross through the negative one. Clear? So, this event is the saddle node bifurcation, we have understood that. Next, as we change the parameter further, there were two fixed points, let us illustrate them in the state space. You have got the state space like so. And here is the 0, we had a fixed point here, and somewhere minus 0.6, there was another fixed point, right. As we change the parameter further, they moved, and when the period doubling bifurcation happened, what was the parameter value, what was the positions, they already calculated, tell me, you have already calculated, x star is equal to 0.3. So, by then from 0 it has moved to 0.3, and whereas the other one moved, never mind, it has moved, all right, it has gone somewhere, it did not stay there, but its eigenvalue did not cross the unit circle, and therefore nothing fundamental happened to this one. Fundamental thing happened to this one, and it became unstable. As a result of which, two fixed points were now born, rather a period 2 fixed point was born, a period 2 fixed point was born. Where would they be located? Now, I told you that you can do that simply by solving the fourth order equation and finding the location of the eigenvalues, finding the location of the fixed points. But logically also you can do. Logically also you can proceed. With logic you can predict where will they be. Let us, in order to understand that, let us understand a few other issues. When we say that you have got a saddle fixed point, a saddle fixed point means where the eigenvalues are such that you have got a outgoing direction, one incoming direction. Now, this was the local linearization, right, and the eigenvectors are defined by this concept that if you place an initial condition on the eigenvector, it will forever remain on that eigenvector, but that resulted from the local linearization. Now, if you go out of the local linearized zone, that means where the local linearization is no longer valid, then obviously these lines will no longer remain straight lines, but still you can identify the lines which have that property that if you start from that from a point on that line, it will forever remain on that line. Okay. We have gone by that argument in the continuous time systems also. Same thing will be applicable here. So, you can in general expect that these fellows should bend and turn and twist and go anywhere they like, right. There is no reason to believe that they will forever remain straight lines. While dealing with the continuous time systems, I gave some names to them. These were the stable manifold and the unstable manifold. So, this one would be called the stable manifold and this one would be called the unstable manifold. In other words, what is the definition of a stable manifold? That if you take a point on the stable manifold and in further iterates it approaches the fixed point, then you would call it a stable manifold. And what is the unstable manifold? What is unstable manifold? If in the reverse iterate it approaches the fixed point, right, because if you are starting from here and if you are going away, how do you know that it started there? In order to really define it, you have to talk in terms of the reverse. How to actually draw them? How to actually draw them? It is not difficult to see that in the close neighborhood of the fixed point, the eigenvectors are tangent to the manifolds, right. Eigenvectors are tangent to the manifolds. So, the way to draw the unstable manifold, for example, would be first to identify the eigenvector, which you can do analytically. Suppose you have identified these as the eigenvector, then take a point along that reasonably close to that direction, so that we know that still the linearization is valid, and then keep on taking iterates. All the iterates must fall on the, but that will not allow you to draw it, because you have noticed that I have put one point here, another point here, another point here. How do you know that it bent this way? So, in order to do that, all you need to do is take a large number of points between the first 2 points and see where they also go, and accordingly you can trace the unstable manifold. You will be able to trace the unstable manifold to the right or to the left, right, and you will have to do two different things in order to locate them. With one routine you will be able to locate the one to the right, another routine you have to locate the one to the left, but the same cannot be done for the stable manifold. It can be done only if, because if you take a point along the stable manifold, further iterates will go into that, and therefore, how do you know where it goes this way? In order to do that, you will need the inverse of the map. You will need the inverse of the map. Therefore, the stable manifold, immediate conclusion is that stable manifold can easily be drawn if the map is invertible, else it cannot easily be drawn. There are routines, people have written routines for that, but nevertheless they are somewhat complicated stuff. I am not going into that, but stable manifold will be, you will be able to write a program to draw the stable manifold and unstable manifold if the map is invertible. What do you mean by invertible? What you mean is that x n y n, this gave x n plus 1 y n plus 1 uniquely. Now, if you know x n plus 1 y n plus 1, do you know x n y n uniquely? If you do, then it is an invertible map. If you do not, then it is not. Just refer to the situation in one dimension. You have the logistic map given as this. Is it invertible? No, it is not, because for every value of x n there is a unique value of x n plus 1, but for every value of x n plus 1 there are two values of x n, right. So, it is not invertible. Similarly, is the Henon map invertible? Just try to work it out and tell me, is that invertible? Is this map? Oh, this is the second iterate here. So, in this case your problem would be, can you find out x n y n in terms of x n plus 1 y n plus 1? Can you write it down as an expression? If you can, fine, you are through. But if you lead to a plus minus term, you are not through, because it will lead to two possibilities. Clear? Now, these stable and unstable manifolds play very important roles in determining the dynamics. Therefore, these concepts should be very clear, otherwise you will not be able to go ahead. This should be very clear, because many things in dynamics of such discrete time dynamical systems depend on the structure of the stable and the unstable manifolds. In case you have got a stable fixed point with real eigenvalues, both would be stable manifolds, right. If you have a repeller means both the eigenvalues outside the unit circle, but real. In that case, you will have both the unstable manifolds. You will have stable and unstable manifolds in case you have saddle, and that is why again you will find that much complicated and interesting dynamics happen in systems where there is a saddle fixed point. That is at the root of chaos. I will come to that later. So, in the next class we will further elaborate on these ideas of the stable and the unstable manifold.